And you're back for the second half, or the last part of Chapter 4 of Explaining Psychological Statistics by Barry Cohen. So the Chapter 4, we've already talked about density curves and the normal distribution. We've practiced how to use the z-table to do calculations to find areas under the curve, probabilities, and percentile ranks. So now we're going to take the information that we've learned about the normal curve and we're going to go into theory mode again after all that application, and we're going to learn why that was so important. Okay. So this was brought up in the last video, but we're going to frame it in research terms right now. So as a researcher, you often have a hypothesis or a question about an entire population. Now that population can have specific inclusion criteria. Like I might not be interested in all second graders, but second graders that are minorities with autism. So however you define your population that you are trying to study, it is usually so vast that we're not able to capture it all. And this can be because it's just literally impossible, or because we have restrictions of budget, of time, of energy, and resources. Nevertheless, we can talk about measures of center and spread and all kinds of things as they apply to the whole population, as well as just to a particular sample that we have access to. In general, we're going to use a capital N in some formulas to mean the population sample size, but more often we use a capital N for the sample size and a lowercase n for subsamples of the population. And that's per good old APA. But for the mean, we're going to use the Greek symbol mu for the population parameter mean, or if the mean we're talking about is the average of a sample, we're going to use x with a bar on top of it. For variance, if it's the whole population, again, a Greek letter, the sigma squared, and if we square root that, we get the standard deviation. So standard deviation is sigma without the square on it. Variance has the square. So the Greek letters are indicating that those quantities are calculated from the entire population, which we usually don't know, but that's what we want to know about. The sample values that we calculate, we usually don't use Greek letters. We use regular alphabet letters. So the X with the bar on it, the S squared, and the S. So the whole reason we take a sample is to get a better idea of the population. And this process of, from a whole population, capturing a sample, measuring things on the sample, and then using the sample to make a statement about the population, that is inference. And what we're going to be learning through the rest of this class is statistical inference. That means that based on the statistic of the sample, we are going to infer or make a claim about the whole population. So based on the sample statistics, a conclusion about the wider population. Now, this is the whole reason or process by which we do research. We very rarely get the whole population. But we need to keep in mind that a sample is not always a perfect representation of the population. If I take one sample and take the average and take another sample the same way but happen to get different members of the population, I'll get a slightly different average. Each time you go about casting a net to get a sample, you will get a slightly different subset. And that slightly different subset will have slightly different properties, different sample statistics. And so we need to be aware of this because there is some fluctuation between samples just inherent in taking a sample. And so we talk about in this chapter the set of all possible samples, or how much we expect samples to vary one from another. And that's the idea of a sampling distribution. So thus far we've talked about a distribution, but the sampling distribution is what a bunch of samples looks like. And we need to know about how much samples fluctuate from one to the other to know how much to trust or how wide of a confidence interval around our sample we could be, how close we could be to the true population, or how far off we might be. So this process of taking a sample has some randomness to it. So this is the first law we are going to learn. So in science, a lot of times we have hypotheses, we have postulates, we have theories, but this is a law, meaning like law of gravity. Very few laws in science. The law of large numbers tells us if we measure enough subject, and that enough, I'm going to put in quotes because it means slightly different things in different situations, but if we have a big enough sample, the sample statistic X bar mean will be very, very close to the unknown population mean mu. And this is the whole point of taking a sample. The average of the sample should be pretty close to the average of the population. How close? Well, it depends on how big the sample is. How big is big enough? That's the idea of power analysis. So, well, I thought there were some arrows here. So we will get some data on our sample, and if it's big enough, the sample will allow us to make a claim about all the possible values we did not capture. We're going to skip the Shiny app to interact with in class and go to the next key idea, the sampling distribution for the mean. So all of the techniques we're going to learn in this class, t-tests and all the various ANOVAs, and this applies to regression as well, all look at the average. We're doing sampling distributions for the mean because we want to know how a population acts on average. And so the first idea is the mean of the sampling distribution. So if I took one sample and got its average and another sample and got its average, all of those averages together would form a normal distribution. And it's going to have the same center as the population, but the spread is going to be different. The spread will actually be smaller. And how much smaller it is, the margin of error, will be the spread in the population divided by the square root of the sample size. So we're going to watch a video. Let's jump right to this video on this. Now, this is only like 3 minutes long. Real short.
Somewhere in the fields, a brave ecologist is studying wild rabbits. He plans to record the weights of every single rabbit. If he follows this plan, he will notice that most of the rabbits are close to the average and that there are some rabbits, but not many, that are much larger or much smaller than the average. The further from the average you get, the fewer animals there are. This particular bell-shaped curve is called a normal distribution. Sadly, he has to give up his experiment, for it will cost him a fortune in carrots to complete it. So, he changes the plan. Instead of measuring every rabbit in the whole group, he decides to measure rabbits in small groups, chosen at random from the whole group. He knows that each small group won't necessarily be perfectly representative of the whole group. So he measures many small groups and then compares the averages of each. He starts by weighing 5 rabbits at a time, and he finds that the distribution of the average is somewhat bell-shaped. Then he increases the sample size by weighing 20 rabbits at a time, and then 100 rabbits at a time. Surprisingly, as the sample size increases, the spread decreases. The distributions of average weights becomes more and more normal. What our brave ecologist has just demonstrated is the central limit theorem. The averages of samples have approximately normal distributions. If the sample size increases, this distribution of averages becomes more normal and narrower. What if the population...
Okay, I want to back that up a little bit. There's an important idea that as the sample size gets bigger, the spread of the distribution of sample averages gets smaller. It gets more normal and gets narrower.
Population distribution is not normal to begin with. For example, the distribution of dragon wingspan is known to be bimodal. If an even braver ecologist were to study wild dragons and measure dragon wingspans, the distribution of the average wingspan would still be approximately normal. And again, the more dragons our brave ecologist could measure at a time, the closer the distribution of their average wingspans will be to a truly normal distribution. The distribution will also be narrower. So now we know that regardless of a true distribution, the central limit theorem shows that the average of values drawn from the distribution will always be approximately normal. Furthermore, the bigger the sample size, the narrower the distribution of average becomes, and the closer the mean of the sample gets to the true mean of the population.
Okay, so I'm going to stop that here again. So, even if the population is bimodal or skewed or not normal, the averages of repeated samples will be approximately normal. And the bigger the sample size you take, the more normal that distribution will be, and the narrower the spread.
This is why sample size matters so much in any statistical analysis, whether it is a political poll or evaluation of a medical procedure. There is something very special about the normal distribution. Not only do many things we measure in biology follow a normal distribution, but it also crops up when we look at estimates of variables even when the variables themselves don't have a normal distribution, as we saw with dragon wings. Because of this, we can use the normal distribution to test ideas about the world even when the underlying variables don't follow a normal distribution. My name is Buthikrit.
Okay, so here's my figure. If the population that we're studying, like the rabbits, is already normally distributed, then the sampling distribution is guaranteed to be normal. The two will have the exact same center, but the spread of the sampling distribution will be narrower. How much narrower? Narrower by dividing it by the square root of the sample size. And this idea of the standard deviation of the sampling distribution is also known by another name. It's standard error. And so it's a very similar phrase. Standard is in both the names, but standard deviation applies to the population or a whole sample. But if we're taking multiple samples or thinking about multiple samples, the standard deviation of the sampling distribution, it would be a sigma with a little x bar, or we call it the standard error. Now, if our population, like they were saying, dragon wings, is not normally distributed, the central limit theorem, it's not quite a lot, but it's pretty darn strong, still applies. So here I have the population, as if we could get it all, of all customer calls to a bank in a single month. And the raw data, the x values, the length of those calls in seconds, is definitely not normal. It's right skewed. But if I take a random sample, say 80 of those calls, and calculate the average of those 80s, and then I take another sample of 80 and calculate their average, and repeat it over and over and over again, the sample averages, even though the population was skewed, the sampling distribution is very normal. And it is now less spread out. Okay, let's get past that. So, the central limit theorem tells us that when we take samples, the bigger the sample, the more normal, but the distribution will still be centered at the same population average. So, here we have a population distribution. So, this is like a picture of what the calls would look like. It's a J distribution with a mean of 1. Now, if from this distribution, and you can think of the population is all samples size 1 because they're all individuals. So this population distribution, if we were going to take from that very skewed J-shaped curve, if we were taking samples of size 2, just 2, that's a pretty small sample, and calculating the average of each pair and putting them back and getting another pair average, the distribution you can already see, even with the sample size 2, the shape of the distribution is becoming approximately normal. Now, this, even though the raw data, the population is totally skewed out the wazoo, by the time we take a sample size of 10, we can see we're getting a fairly normal looking distribution for the sample average. And this last one in the bottom corner, D, should be sample sizes of, I think, 50. That's a typo there. And again, we're seeing not only is the distribution becoming normal, but it is also becoming narrower. And that's the central limit theorem. So when a sample size is large, the sampling distribution for the sample mean is approximately normally distributed around the mean of the population with a standard deviation less than a factor of the square root of n. Okay, we're going to go back to the one more example, and then the slideshow will be over with a little bit of our code, just a little bit. So here's our example. We're going to go back to our chapter 4 example with our school population that had heights of students measured, and we're assuming, that's a big assume here, this is not what we do in research, but we're assuming we have heights follow a normal distribution with a mean of 1.4, that's mu, and a standard deviation of 0.15. And now we're going to ask some questions that are getting at the p-value idea. For number one, what's the probability a randomly selected student, that would be a single student, has a height of more than 1.6 meters tall? Now, number 2 is almost the exact same question, but look at how subtle the wording is different. The probability of a randomly selected sample of 16 students has an average more than 1.63 meters tall. So number 1 is asking about a student, a randomly selected single student. Number 2 is asking about the average of a sample of 16 students. That makes a difference when we're taking a sample. So here I've taken my normal curves. Now, whether we're taking one student or a sample of 16 students, the distribution is always centered on the population average, which in this case is 1.4 meters. So I'm going to label the center. The center of the distribution is the same whether we're talking about the probability distribution for a student or the probability distribution for the sample average. Centers are the same. That's the first part of the central limit theorem. The second part says that the standard deviation of the population as a whole, in this case 0.15, for the sampling distribution is narrower. How much narrower? Well, you take the original standard deviation of 0.15 and divide by the square root of the sample size. So the key here, sampling distribution has a sample, so it has a sample size associated with it. So I've written several different things down here. For the population distribution in red, we use either the sigma by itself or a sigma with a little x as a subscript submarining down on the sigma. If we're talking about samples instead of individuals, for samples, the standard deviation would be sigma with a little x bar. For the sampling distribution of the mean, the standard deviation is sigma with an x bar, or it's called the standard error. And this is the last new bit in the homework. So both of these questions use a height of 1.63 meters tall. So to find a probability, we need to go to our z-table, and to do that, we need a z-score. So for both 1 and 2, we're going to convert 1.63 meters tall to a z or z score. Remember that standardizing is a two-step process. Subtract the average. They both have an average of 1.4, but the standard deviation we're going to divide by is different in both of these cases. So if we're talking about an individual student, the z-score, we're going to subtract the center, the mean of 1.4, but we're dividing by the population sigma of 0.15. It's different when we're doing a sample because the standard deviation is no longer 15. It's smaller by a factor of the square root of 16. So we have to divide by, in this case, 4, because the square root of 16 is 4. So we get, even though both 1 and 2 have the same heights in meters, they have different z-scores. So in number 1, our z-score is just over 1.5. But in number 2, our z-score is a whopping 6. Remember our 68, 95, 99.7 rule? 3 standard deviations either side of the mean captures 99.7% of the data. And so to be 6 standard deviation, that's way out there. So we're going to go to the z-table, and for both of these, we are going to find the areas in the table. But again, we need to look at this wording. It says we want to find probability, so that's going to be a percentage written as a decimal, specifically more than this height. Both of these questions state more than this height. So before I rush off to that z table, I'm going to shade my curves. So in both of these, I would shade above the 1.53 and the 6.13. It's going to be the shaded above. So this is going to be a z-score or beyond the z-score. So when I go to my table, I'm looking at my two z-scores in the z column, and I'm going to go over and look for the beyond z. Now, for the individual student, a z-score of 1.53, our beyond z is 0.0630. But there's a little hitch. For this sample of 16 students, our z-score was more than 6. That's a big number. And if you go to the z-table, the z-table goes up about every 0.01, and then it gets to 3. And when you get beyond 3 standard deviation, you don't have a lot of data. So the textbook table kind of starts skipping after that. So after you get to a z-score of 3, it jumps to 3.2, 3.4, 3.6, 3.8, and the last entry is 4 in this Z column. And they put some space in here to kind of like clue you in, oh yeah, we're skipping values at this point. But the last value on our table is 4. So how in the heck do we look up a 6.13? That's a huge Z-score. And the answer is we don't look it up. But again, we're looking at that tail, that beyond Z area. At 4, if we go out 4 standard deviations, that tail is tiny. It's 0.00003. So if we were even to go out further, that tail is going to be smaller than that, which is really, really small. So for the intent of this class, we can say that that tail area is less than 0.0003, and that's good enough. Now, when we write APA style, yay, APA, we're going to always report decimal places to 3 digits. Again, most numbers, almost all numbers to 2 decimal places, except for p-values to 3 digits. So for in the case of number 1, since our tail area, our beyond z was 0.0630, we're only going to use those first 3 numbers after the decimal. In part 2, since our p-value is so tiny, this is the exception to the equals 3 digits rule. You would report that as less than 0.001. So we still have 3 numbers, but instead of being equal to something, we say it's less than the tiniest amount we're going to report. And this is the way we report p-values. And so this will tie in with every other chapter that we go forward with. We knew we were going somewhere with all these table nonsense. Okay, so the last thing we need to do is look at how we're going to do this, anything with this in R. And really, there's not a lot for us to do in R with this chapter. We had a lot of hand calculations, and I know they're not your favorite. They're not my favorite either, but we need a feel for z-scores and p-values, probabilities, and percentile ranks before we move on. So the only thing we're going to learn how to do in R with these standardized distributions, we already know how to make histograms, but now we're going to learn how to make an actual z-score in R. So to show this, I'm going to use not Eno's dataset, but the Cancer dataset that we used last time. And so this is on Canvas if you want to get it and play around with it, but you can just watch me. So I'm going to read in this Cancer dataset from SPSS and kind of tidy up the variables that are factors. So we've already seen how we can pipe the data set into furniture table 1, and when we tell it a variable name, it will report, now age is continuous, so it'll report the mean and standard deviation. Now this data set is not a whole population, so these values are X bar and S, the standard deviation S. And the average age in this population from this study is 59.6 years with a standard deviation of 12.9. The only thing we're really going to do is use this new command out of base R called scale. Scale converts any variable to z-scores. So to show you, I've taken that same data set and then I've given it to dplyr to mutate, and I've created 2 different mutate statements. One takes the age variable and manually subtracts that average I just found and divides by the standard deviation. So I've typed out with parentheses, subtract and divide, how we find a z-score. Remember, two-step process. Take our number, x, whatever it is, subtract the mean, and divide by the standard deviation. Preferably the population values, mu and sigma, but if we don't have them, we can use the samples values of x bar and s that we got in our furniture table 1. So here I've done it manually, which you're free to do, but you have to find out what the mean and standard deviation are before you can. Or we can use this scale command. Now you'll notice that the first variable I named age with a lowercase z, and the second variable I'm naming age with a capital Z, so I can tell the part. Because remember, R is very concerned with capitalization, so it will know that these are two separate variables. So I can create a standard variable by just telling R to scale the age variable. Scale will make it a z-score. So I've selected these variables, the subject ID, what treatment group they're in, and then the 3 age variables. The original age, the age with a lower z, which I manually created, and age with a capital Z, which I calculated with the scale value. And if we look at this data set, you'll see that both age z scores are pretty much identical. There's a little bit of a difference here on some of these, and it's because I only used the mean and standard deviation out to 1 decimal place. If I had used the mean and standard deviation with multiple decimal points, these two age z-scores would be identical. And to prove that these are z-scores, z-scores, we can take the data set, and after we make that scaled score, we can throw that back into table 1. So here I have my sample of 25, and I can see that my original age variable had a mean and a standard deviation, but when I make it into a z-score, it's standardized. All of a sudden we have a mean of 0, standard deviation of 1, and that's the standard normal curve. Now, it's not guarantee that I've changed the shape and the shape will magically be normal, but I've standardized it so that the units are in terms of standard deviations. And in fact, I can show you that if I take that data set, make that age z-score, and plot it in a histogram, that's not normal. So again, reminding you, if you use the z-score formula for anything where you subtract the mean and divide by the standard deviation, you will change the center to 0, the spread to 1, but you will not change the shape. Standardizing does not mean normalizing. It's kind of a common thread. All right, so I'm done with the lectures. This one was definitely shorter than the other one. I'll get this posted and I'll see you in class.